Anthropic recently accused 3 Chinese AI labs of running, quote, an industrial-scale distillation campaign against Claude. 24,000 fraudulent accounts, 16 million exchanges, DeepSeek, MiniMax, Moonshot, all the major AI tools from the Chinese AI companies, all allegedly extracting Claude's capabilities. Now, there's a lot of discussions about the politics, and of course, since this has come out, Anthropic's got bigger problems than this. But I wanted to understand how the process worked, and I built the whole pipeline myself. One actual API key, about 104 prompts. I spent, a whopping $61. And what I found was interesting, so let's take a look. My name is Ken Cousin, and welcome to Tales from the Jar Side. Today I'm going to show you what distillation actually means. I'm going to walk you through the code, run parts of it live, and then we'll look at the results together, because what distillation does and does not transfer to a student model is the part that nobody seems to be talking about. So let's start by talking about what distillation is. It sounds exotic, but the concept is pretty straightforward. The idea is that in distillation, we train a smaller student model to imitate the larger teacher's model with the outputs, often using the teacher's full probability distribution to get a faster, lighter model with similar behavior. Let me say that another way. The expensive model's the teacher, and in this particular case, the one I'm going to use is Claude Sonnet 4.6. Then we have a small, cheap model, the student. The one I'm going to use is Qwen 2.5 with only 1.5 billion parameters. That's really small. We'll get into that in a moment. But the idea is you train the student on the teacher's inputs and outputs, and then the student gets better at that particular set of inputs and outputs. Now, to give you a sense of scale for the parameter counts here, because these numbers come up constantly and they're easy to lose track of, think of it this way. If a model has a single digit in the billions of parameters, 7 billion, 1 billion, something like that, that's very small. They're not very powerful. And the smaller we get, the more the answers will be ranging from mediocre to terrible. If you're in 2 digits, 35 billion, 70 billion, something like that, those are decent models that you could run on a reasonably powerful laptop or a desktop GPU. That's where a lot of the popular open source models live, things like Llama and Mistral and some of the bigger Qwen variants as well. If you get up into 3 digits, 100 billion, 500 billion, now you're almost certainly looking at a cloud model, and the results will be substantially better. It probably won't run on your own hardware, but the answers are hopefully worth it. The models like the current frontier commercial models are way bigger than that. GPT-5 is rumored to have between 2 and 5 trillion parameters. So we're jumping up another couple of orders of magnitude. So our teacher is going to be Claude Sonnet 4.6, one of the frontier models, but not Opus 4.6, something smaller than that, likely in the hundreds of billions of parameters. And the student will be Qwen 2.5 with 1.5 billion parameters. Single digit, bottom of the scale. Now here's the basic process that I'm going to run through with distillation. I started off with 32 basic prompts, targeted prompts that are all about coding. I'll show you those in a moment. And in order to get a decent number of prompts, to expand that to 104, I have these extensions I add onto it, things like, generate a set of test cases, or be sure to enhance the documentation, or come up with specialized exception handling, that sort of thing. So by combining the extensions with the individual prompts, I boost the number up to about 104. Then I run them all one by one through Claude Sonnet 4.6 and build up a JSON-L file that has inputs and outputs. So those are the, quote, right answers, if you will. And that will be the training data that I will then supply to Qwen 2.5. So the fine-tuning process is going to use a specialized technique known as LoRA training. This is probably not exactly what the Chinese models are accused of doing, but it's something I could run locally, and I'll give you an idea what we can possibly accomplish. That will produce a distilled model. And then step 3 is we'll compare them. I'll put in the Claude answers, and I'll also run questions through both the base model without the distillation process and the distilled model and compare them side by side. So see how much of an improvement we got. And then to judge the overall competition, this is where I'll use Opus to give some quantitative sense. It's still kind of hand-wavy using a judge like that, but it's quick, it's easy, and it'll give us nice results. Now, the first thing to keep in mind, this is not a secret technique. This is standard industry practice. For example, if you've ever used GPT 5.2 or any of the GPT 5 models, you see how they're broken into the top level GPT 5 model and then a GPT 5 mini and a GPT 5 nano. Basically, everybody knows that the mini and the nano model were distilled from the full GPT-5 model. Anytime you get a model family like that, like with Claude, you have Opus and then Sonnet is smaller and then Haiku is smaller still, they were distilled from the larger flagship models. In general, there's even an API to do this. So this is not abnormal. This is not unscrupulous. This is something that everybody does. It's how model families work. So the question Anthropic is raising is not whether distillation is ethical or moral or should exist. It's who gets to do it and when. It gets a little bit dicier there. At any rate, let's go on. Now, this script right here in the GitHub repository, link in the description, is called Collect Teacher Data. So this is the one that's just going to collect the data here. So I start off by saying, here are my coding prompts. Get this out of the way. And you see they're basic prompts from data structures and algorithms like implement Dijkstra's shortest path algorithm in Python or what have you. And then some practical coding tasks. Write a Python function that parses a cron expression and returns the next n scheduled runtimes. Here's some from DevOps to write a bash script or a Docker file. Here's some SQL requests. Write a SQL query to find the second highest salary in each department with windowing functions. Here's a few Java ones. And here's some questions to explain a process. What's the difference between composition and inheritance? On and on. So there's the basic prompts. And again, I've got about 32 of those. That's not really enough. So here are the modifiers. This one is about adding comprehensive error handling in edge cases, or include unit tests that cover normal cases and edge cases, or analyze time and space complexity. This one is implementing alternative approaches. This one's walking through your reasoning step by step and making this production ready with logging, type hints, and doc strings, etc. This process of generating all of these individual prompts is the basis of what Anthropic is describing the Chinese labs as doing. The difference being is that this winds up for me of about 100 prompts, whereas they had millions of variants. We're doing the miniature version, but the technique is the same. Now, even though I can show you the code here that runs everything collecting the responses, this took a while because I had to run all those prompts through, collect all the answers, and to keep from running into problems, I have a half-second delay in between each one. I'm not going to demonstrate the process because it took roughly half an hour to run through. The basic idea is simply to pass in the prompts, use the Anthropic API to process each one and get back the results and save it into a file, which I did. But again, the basic estimate of what this cost me was $1.61. That's partly why I used Sonnet to keep the cost down. I wanted something better than Haiku, but I don't need the power of Opus yet, not for all of this. Now, to give you an idea how this is going to scale, for me, again, it took about $1.61. A small campaign of 10,000 prompts by that same measure gets up to $155. A million prompts would take it up to 15K. And then what DeepSeek and MiniMax have supposedly done is use 16 million prompts, which would cost them roughly $250,000. So 248,000. It sounds like a lot, except of course, training the frontier model from scratch costs $1 billion and months of processing. Here we're just running questions and answers through it to try to distill it down to something simple. Now, every one of those is a paid API call. So regardless of what's happening, the bottom line is Anthropic got paid for all this. They probably made at least $250,000 from it. So not bad. If you're going to get attacked, I suppose getting paid to be attacked is something anyway. Okay. Now let's talk about the fine-tuning. Now, before I get into the actual technique, let me show you the import statements here. So we've got a few things I want to highlight. There are 4 libraries that were used a lot. The Transformers library is very popular and is used throughout many libraries on Hugging Face. And that one loads the model and the tokenizer. Data sets, of course, holds the training data. This PEFT thing down here, the parameter efficient fine-tuning, provides the LoRA implementation. And then TRL is the training library using SFT, which is supervised fine-tuning implementation. These are all very standard tools. If you search for how to fine-tune an LLM with LoRA, this is the stack you're going to find on virtually every tutorial. Now, the thing to pick here is a small student model that we're going to try to fine tune. The one I'm using is that Qwen 2.5 with 1.5 billion parameters that's already been through the instruct process. You could use Tiny Llama, you could use the 500 million parameter one. I tried that because it was quicker, but it's still a bad model even after the fine tuning. If you've got the RAM, you could use, say, Phi 3 Mini, which is 3.8 billion parameters. It's going to take a little longer, but it might actually get something good out of that. Now, the model I'm using with only 1.5 billion parameters, generally I consider a model like that mostly just good for a laugh. You run into problems very quickly. You could ask it anything unusual at all, and it's going to give you serious problems. But that's kind of the point. If distillation can make even a model that small noticeably better, it gives you an idea what it could do for the better ones too. So let's skip down to the LoRA section here. In principle, with fine-tuning, I could try to train all 1.5 billion parameters, like the original process does. There's a feed-forward loop and a back propagation loop and all the error handling and the attention mechanisms and all the things you learn about if you dig into how this is done for real. But for me running on my own laptop, that would be huge and expensive. That would be a serious problem. And not only that, it's going to overwrite everything the model's already learned. So instead, I'm going to use this process called LoRA, which stands for low rank adaptation. So here's the basic idea. There's your original matrix, which is the full size 1.5 billion parameters. Here we have that same matrix, but we're going to add in this smaller matrix times this smaller matrix, where the rank here, the smaller dimensions, only 16, say, and the result is when we multiply it all together, this is a matrix of parameters that will be added to the frozen original, so we don't change the original, and we only are tuning about 0.1% of the total parameters, about 1.7 million out of the 1.5 billion. That's the basic idea. So we don't need all the degrees of freedom of the full matrix because we're only going to train it for these basic programming tasks. So the change needed to shift the model's behavior on coding prompts can be described by a small number of patterns. That's what the low rank part of LoRA means. And the update's simple enough to compress without losing all the detail. We apply this to the 4 attention layers in each transformer block: the query, the key, the value, and the output. Those are layers that control what the model pays attention to, as they say, when generating each token. By adapting just those layers, we're changing the model's style and focus without touching the feed-forward layers that store its factual knowledge. If that's a little unclear, there are many tutorials on YouTube and on other places that will explain this entire process in detail. Especially take a look, for example, at the Manning book on building your own large language model from scratch. Now, again, the reason we're doing this more limited mechanism is so that I could do it on a reasonably powerful consumer laptop. I actually have an M4 Max MacBook, and I'm able to run this whole thing in about 11 minutes. No cloud GPU, no rented compute, just everything runs locally. So that's not factoring into my cost, except indirectly in the cost of the laptop. Again, that's not what the Chinese labs did. They don't need this shortcut. With data center GPU clusters and 16 million examples, they could do the full fine-tuning, update every parameter in their own model. That means the capability transfer at their scale goes a lot deeper than what we're seeing here. What we're going to see is LoRA is going to transfer the style of the output, whereas full fine-tuning at industrial scale could probably pick up a lot more detail. It also means that our distilled model should only improve on the kinds of tasks that we tuned it on. Those were all coding tasks in this particular case. When I ask it something outside that range, it should perform about the same as the base model, and we'll test that later. Now, taking a look at the results after the 11 minutes here, you could see that the loss parameter, it came down, but not a huge amount. And in fact, the accuracy, meaning how often the student predicts the same next token as Claude Sonnet, goes from about 78% to about 80%, peaking at 82% partway through. Again, not a huge change, but we only have 104 examples. The effect would scale with data, and of course the Chinese labs had 16 million. At any rate, the entire process runs. Let's look at this in a slightly different way. This is the diagram I really want to show you. This is a radar chart to compare the models. I'm looking at them on code correctness, structure and design, documentation quality, error handling, and completeness. Now, the measures here, the actual numbers, are judged by Claude Opus 4.6. Now let's look at the individual models. The yellow one here, the yellow pentagon around the outside, that's Claude Sonnet. Those are the quality of the answers that Opus assigned to it. The inner red one is the base student, the 1.5 billion parameter model with no training at all, no distilling. And the answers are okay. The blue one is the same as the base model, but with the distilled training. So this is the much better distilled student. And you could see that in some scales there's a big change, and in some there's hardly any at all. The code correctness isn't that different. They still came up with roughly the same degree of correctness. But the documentation quality has a big jump. The error handling is night and day. Even the structure and design is better. The conclusion I'm coming to is that the distilled model learned Claude's vocabulary, custom exception hierarchies, data class wrappers, structured documentation with overview headers. It didn't learn Claude's actual reasoning. It learned to mimic the behavior, but didn't really get much better on the correctness. That's the part that didn't really move much. It transferred the style, not the substance. It's like talking to a grad student who has learned from the professor and is able to imitate what the professor said and how they said it. But if you ask them for depth, they wind up with some gaps. They don't really know. It's shallow in what they understand. Now, in case you want to try out this sort of thing, I've added in this chat script here, an interactive chat that's going to load both of these small models, the baseline model and then the distilled one together. So let me run this script. And you can see both the base model and the distilled models have been loaded. And we've got a prompt here saying, give us a prompt, press enter. So I'm going to ask it, implement a retry decorator that supports both sync and async functions. So let's see what we got. The one without any distillation has a little discussion about it. And there's the async IO and the functional tools. And writing retry with backoff, you could see the method it created, the function and example usage, and so on. A little bit of explanation as well at the end. Not bad. Here we get the distilled model, and this time we're using function tools and time and logging with imports. It defines its own exceptions again, the retry error with an exception, and too many retries with a retry error, an unretriable error, no retry on succession, all this extra documentation as well, putting in the docs on everything. And the problem is it didn't even get the whole implementation done because it ran into my max tokens cutoff. So it was, again, trying to imitate the form, and it just ran out of tokens. So the distilled model spent all 512 tokens in the output, because I limited it to that, on architecture and documentation, and got cut off in the middle of the constructor. So it made a nice little beautiful API, but didn't finish implementing it in what we have. The base model at least gave us some runnable code. I have to tell you that on a previous run, it even had an author of Qwen, Alibaba Cloud, license MIT. Its own identity was leaking through the Claude's formatting. But okay, just training one model's style into another model's brain, if you will. So let's try a SQL one. So I'm going to say, give me a SQL query to find the longest streak of consecutive days each user is logged in. Okay, so let's see what we got. To find the longest streak of consecutive days, you use a combination of window functions and common table expressions, and they go through, and here's the SQL query with the select inside there, max streak as with a select here, and so on, and then an explanation down below it. Now, what about the distilled model? Gave us a select right off the top, and the from with the sub-select inside it with the partitioning and everything, and an explanation for that. That one does look a little bit better, I think, with the distilled model. So not bad. Now, sometimes the style transfer would actively hurt, like the earlier one where it didn't even have room in the output tokens to give an answer, but this one seems to have done a decent job. Now, one more test. Remember I said that because we use LoRA and only trained on coding prompts, the distilled model should only perform about the same as the base model on non-coding related tasks. So let me try that out. So I'm simply going to say, write a haiku about rain. Haiku, again, 3-line poems, 5, 7, 5, and the number of syllables for each one. They are supposed to have something nature related. It's just poetry though, and we'll see what it comes up with. Well, that one came back very quickly, which is nice. Raindrops fall so light. Okay, that's 5. Nature's soothing melody, that's 7. Endless serenity, that's 6. So not even a legal one because it counted wrong. What about the trained model? Raindrops whisper, which is only 4, so we're already off. Silent on the earth's skin, so that's 6. Nature's cool embrace, that's 5. So again, not really that different because we weren't trained on that. So it got what you got. They're close. The distilled version might be a little bit more polished. I don't know. It depends on how you want to say it, but not dramatic differences. You can barely tell which one is which, really. And of course, we shouldn't be able to. We didn't try to train on that. So what do these results tell us? There are multiple different outcomes. There's at least a couple where distillation helped. There's an issue with adding in all the extra documentation and structures, making it run out of output tokens before we got an answer. That's a problem. The style transfer is obvious, but then there's a substance gap. Some that it did seem to be better, and one where the effect isn't really showing up at all, like on the haiku. So the more honest picture of distillation than it works or it doesn't work is a bit more subtle. It transfers the style, the vocabulary, the architectural instincts of the targeted task. It doesn't transfer reasoning or correctness or the ability to finish what it starts. And it fades quickly once you step outside the training domain, unless you do full fine-tuning at the scale the Chinese labs were using. So what does this all mean in the real world? Well, first, the economics. I did all this for under $2. It cost me hardly anything. And now I have a trained model that is, in principle, significantly better than it was before it was trained. And it's still an inexpensive model. I don't have to use Sonnet for questions that are within that training set. The Chinese labs did this at 16 million scale because the incentives are overwhelming. $1 million in API calls to extract capabilities that cost billions to develop. Anthropic's countermeasures will probably slow it down, but they're not going to stop that. In fact, the economics are so lopsided, you're actually encouraged to use more distilled models for simpler tasks. It's the same reason you use GPT-5 Mini or GPT-5 Nano when you don't need full GPT-5. Distillation transfers the style, but not the substance. There isn't the same depth. If you can get away with that, great. If you need more understanding, if you need it to be able to route around problems or deal with other issues, then yeah, you need the extra depth that comes from the full model. Hopefully this helps you assess how you would evaluate models for your own use. If a small model scores really well on the benchmarks, ask, was it trained on the benchmarks? What's it actually good at? Is it good at tasks you plan on doing, or is it good at looking like it's good at tasks? Distilled models would score very impressively on benchmarks that were based on that handful of questions that we gave it to learn. It would score very poorly on, is the code right? Does it actually run? Other issues. The surface and the substance are not the same thing. Now, a couple notes about the headlines. Anthropic framed this as a, quote, attack and tied it to national security and export controls. Given developments between them and the Pentagon, maybe it's not surprising why they decided to take that tack. They had negotiations coming up and they wanted to raise that flag. Did it work? I don't know, but it's interesting. The terms of service violation and the fraudulent accounts, yeah, okay, those are real. After all, Sonnet was not available in China, and they had to go to all this trouble to set up this Hydra network of fake accounts that would do the queries and then get shut down and then spin up new ones and do new queries and everything. But the basic distillation process and the technology, it's straightforward. It's relatively easy to do. The entire demo, the 3 steps, the interactive chat tool, the code, the visuals, all of that, if you wanted, is all on GitHub, link in the description. You could run it yourself. You could tweak it, try it however you like. Step 1 is the one that'll take time and cost money because that's the one that's actually feeding questions to Sonnet. So you'll need the Anthropic API key. Step 2 runs on any Mac with Apple Silicon or with a machine with a GPU. So it checks for either one of those. If this was useful, if you now understand what distillation actually is and what it can and cannot do, please consider subscribing. I try to do these technical deep dives on a regular basis whenever something in AI or software development, especially in Java, deserves a closer look than the headlines are giving it. Let me know in the comments what prompts you would test with if you ran it yourself. I'm curious what domains people want to see versus on the base versus distilled comparison. Thank you very much for watching, and I will see you in the next video. Take care, everybody.